We talked on Monday about binary classification. Yes, we talked about using the sigmoid function, right, which will take something from negative infinity to positive infinity and shrink it down into the range 0 to 1, which is good for representing like probability, which is good for binary classification. And then we looked at a loss function, which is the cross entropy loss. And we basically said that was equal to negative y log y hat plus 1 minus y log 1 minus y hat. And particularly what we looked at is the desirable properties that happen, right? That the more y and y hat diverge from one another, the higher the loss, which is what we. And then when y and y hat are identical, the loss goes to 0. Right, so today what we're going to talk about is optimizers. So if we go back to our picture here, where we have x coming into f, y hat coming out, this coming into a loss, along with y. Here's where we're working today in the optimizer. Then, what changes have we seen in the optimizer already? Right? Normally, we were just using theta equals theta minus the learning rate times the gradient, right?
Yeah, we saw the penalty from last time.
The penalty, yeah. So the ultra regularization can be implemented as a weight decay in here. So that's one change to the optimizer. The L2 regularization we can do in the loss function, or as we saw, we can also do it in the optimizer. Okay, that's weight decay. Now we're going to look at a lot of other changes we can make to the optimizer. So if we think of a marble rolling down a hill. Okay, so let's try it. With a few little bumps, or something like that. Okay, and we'll start this up here. So our marble, and again, this is sort of representing the loss, and this is representing some parameter. And so as the parameter changes values, the loss changes. So let's say our parameter is up here. We would be going to the right to reduce the loss, of course. And we go down, and could we get stuck here, Ezra?
Yeah.
If what? How could we get stuck here?
If the learning, if the steps were too low.
Yeah, if we were taking tiny, tiny steps, that's a possibility. So if the learning rate's too low, we could stop here, and we know we want to get down to here. If you put a marble up here, would it get stuck in here? Probably not, because it would accumulate some momentum as it was going down, and that would take it and just sort of drive it over the ups that it needed to go up. That's the idea of what we're going to do with what's called momentum. So the idea is we're not going to just look at the immediate gradient. We're going to look at some accumulation of gradient. So what we're going to do is we're going to keep an exponential moving average of the gradient. So for example, if we were here, and then we took a step that, say, like took us to here, and then a step that took us to here, and then a step that took us to here. Right, so we're here, and here, and here. We're not going to look just at this shallow gradient. We're going to actually say, we've actually accumulated a succession of gradients, some of which were higher. So our average is higher than we are now. Right? Our recent average is higher than our current value. And so we're going to update our parameters based not on our instantaneous gradient, but instead based on our average. So, I'm going to find something new called, let's say, V for, you can call it M for momentum, V for velocity, however we want to do it. So we want to do an exponential moving average. So how to do that? Well, we know we want to take into account the previous average that we have. And we're somehow also going to have to take into account our current gradient, right? So our current gradient, which is partial L partial theta. I'm going to look at this V sub t as a vector. Just as our theta can be considered a vector. So we actually have the components, partial L theta 1, partial L theta 2, partial L theta 3, and so on, but they're going to just accumulate together in a big vector. So this will be a vector, this will be a vector, this will be a vector, all of the same size, the number of parameters. And what we want to do is take some of this and some of this. Basically, we want to take a weighted average of this. A weighted average just means we need some amount here. Let's say beta amount here. And if we're going to use beta of that, let's use 1 minus beta of this. Okay. Where beta is, Nick? What sort of a thing?
That would be a hyperparameter.
That would be a hyperparameter, yeah. And a common value might be, let's say, 0.9, maybe. So we care a lot about what's happened in the past. And so now we've got this. This is like a gradient. It's just an average gradient. And we can then use this to update our parameters. So we can say theta at time t equals theta. I guess I need to have a plus here. Sorry, can't just, yeah, we definitely want to be multiplying, right? We're adding together. So normally here we have theta minus lambda partial derivative, right? The instantaneous derivative. And we're replacing the instantaneous derivative with our average.
Could you also
Yeah.
wrap the penalty into this entire expression?
Yes, we would probably want to wrap the penalty, well, first, let me back up a second. So a penalty would normally belong in our loss function, right? So that's where we would be putting our penalty. The question perhaps is, if you're using L2 regularization as your penalty, will that propagate up into here? And it's a simple matter of algebra. I don't know. We'd have to look and see. So it might move easily into there, and it might not. Other question? So let's say this goes up like this. Without the momentum, if our learning rate is sort of about this big, I don't know quite how to show it, but let's say we are doing a, we're here at this point. We're going to go down and to the right, without momentum. And we'll go maybe here to here. And then, Ali, in what direction are we going to go without momentum? Yeah, we're going to go back to the left. Let's say maybe like that or something. In the case of momentum, if we came from up here, then we were here in the past. Mo, what's going to happen when we get here?
Just keep going with that.
Yeah, we're going to kind of keep going up. We're going to be having a positive portion here, right? Our old momentum is going to be saying go to the right. Our new value over here is going to be saying go to the left. So we're going to go up, we're going to kind of slow down, and then we'll go back. Just like a marble would. Not exactly, but roughly. Concept make sense? So what does this give us? This says, let's look at this particular example. a second. We do, yeah, so let's say, remember our contour map? Right, where this was representing the loss in 2 dimensions. And so we had our horizontal theta and our vertical theta. And if we were, let's say, over here, then we're going to end up, we have this steep gradient in the vertical direction and a shallow gradient in the horizontal direction. And so therefore, we're going to kind of go as our weight gets to the center without momentum. Let's look at the same picture with momentum. We start here, and we're going to go here, right? But what's going to happen in the horizontal direction on the next step, Rory? So we're here, we have momentum, I mean we have none to begin with, right? So we have 0 momentum to begin with. We go here, and now we're on the next step number 2. So the gradient, the instantaneous gradient says goes this way. What happens to the horizontal movement that we actually do?
Horizontal meaning like.
Horizontal meaning this way, yeah. So this is the original horizontal movement from here to here, right, the component. Is our component going to be higher or lower than that if we have momentum? Higher, he says with confidence. So let's, I'm going to make this a little more clear that we actually had a horizontal component here. That's an important piece, right? So our initial vector was here. So this was, let's say, v sub 1. V sub 2 is going to be a linear combination of v sub 1 plus, this is our partial derivative. So this is our g, let's just call it. Okay, g for gradient. But we're going to basically be adding these two together, right? So in the horizontal direction, we're going to actually end up with an x component that's like this. So instead of moving this amount, we're going to move this entire amount. So we're going to end up in a horizontal direction, moving that amount. Okay? Because we're not moving in this g. We're calculating the g, but our movement is going to be the g plus our accumulated gradient. Does that make sense?
In this case, are we assuming that they're weighted equally then?
I'm just kind of waving my hands at that. Yeah, sort of. Let me think about that a second. So we are going to make this better, but we're not going to make it better in the horizontal direction. I'm just realizing. So in the horizontal, because what we're computing is an exponential moving average. Okay? This average of the horizontal components, each horizontal component is about the same. Right? Here. So therefore, the average is going to be, no matter how much I weight it, about the same. So, just forget what I said, but we're going to look at the vertical and it's going to be a lot nicer. All right?
So if there
Well-
was more of a difference in the horizontal, then averaging it would increase it, like if it bounced at a different rate, because you're saying that.
Yeah, if each horizontal, if sometimes it does big jumps, and then the others it did normal jumps, then what we would end up doing is having it smoothed. So we wouldn't have as big a jump at the time that we're making a big jump, but we'd have larger jumps at the times that we're making smaller jumps. Really just think of it as an average. The average is not helping us too much here when we're going the same direction. But what it does help is when we're switching directions. Okay? Because when we're switching directions, the average vertical is about 0, right? It's maybe going up. We can try and make it go up a little. Because we know we want to end up at the basin here, right? So eventually it should end up in the middle. But what should happen is we'll end up with a much smoother, kind of like this. Could be roughly what we end up with, where we're going no quicker in our horizontal direction, but we're staying so much smooth in our vertical direction. Does the concept make sense? Okay, any questions? We have this vector diagram that we're using for this, we can use. So we can say, let's say this is G, our instantaneous partial derivative gradient. And we have, let's say this, which represents our V, okay, our accumulated gradient. And what we're doing is basically taking this G, so this is V sub t minus 1, and this is G evaluated at theta time t minus 1. So we're just taking the old parameters, right? We haven't updated the parameters yet. We take the current old parameters, we find what the derivative is, we take the old v sub t minus 1, and then we do a weighted vector addition. So we take this, move it up here, you kind of end up, let's say, that's our endpoint. So this is our v sub t. So that's just this vector addition. With the important point being that when we're evaluating this partial derivative, right, we're evaluating it at a particular value. So a particular value of theta. The value of theta that we're using is this is evaluated at theta time t minus 1. Just say time t minus 1. Questions on that? You can keep in mind, let's go back to this picture here. Let's say that this is v sub t minus 1. So we are right here. Our derivative here, null and positive or negative.
Where were we at?
So we're right here.
So we're going down.
Yeah, so negative, right? So therefore, if we add this, it's a negative slope, and so therefore, we're going to want to be increasing our parameter to decrease our loss, right? So we're going to be going to the right. So this one's going to the right, and the momentum is always taking, also taking us to the right. So we are going to be basically going here, and then some more amount based on how much this gradient is. And so we're going to end up somewhere up here. However, here's what we could consider. We know we're going to be moving by an amount of the old momentum. So we're moving sort of by an amount, a weighted amount of the old momentum and the gradient. What if we kind of looked ahead? We looked ahead and said, well, if we moved over here, what would the gradient be? Right? So rather than looking at the gradient now, say we know we're going to be moving anyway, let's just look ahead just a little bit and see what the gradient is there. And in this case, that would work well. Because we would say, wait a second, we're going to be overshooting. We don't think of it that way, but we actually are overshooting. And although our gradient's negative here, where we're going to, the gradient's going to be positive. So we would then actually decrease this and end up somewhere in here. So from a vector point of view, we're saying is, we're not going to do this. Instead, we're going to, again, take v t minus 1 and look at the gradient here. So evaluate here. That is, take our parameters, add in v sub t minus 1, and then look at the gradient there. Good question.
How is this going to help us avoid the local minima though? Because like you could get stuck in a local minima, right?
You can always get stuck in a local minimum. The fact is, so I guess the problem is if you're coming down here and you've got your momentum and then you hit the right side of this local minimum, it's gonna slow down your ball and might be enough to pull you back. Part of that is going to be what is your overall learning rate, and part of it's going to be what is your beta here. Right? If your beta is fairly large, we're saying we count the momentum a lot, and we don't count our current gradient that much. And so that's kind of what we would tend to do there. Because if our numbers are kind of, if they're looking this wide, we're going to be skipping kind of right over that. And this is so big compared to the other that we'll exceed that local minimum. But we need to be making jumps enough so that we get at it. So we evaluate our gradient here. If we evaluate our gradient here, it might not be exactly this vector, right? It might be somewhat different. It might be, for example, I don't know, this vector. So this is our G evaluated. So it's called our G prime as opposed to this G. So this is our look ahead G. And so we end up, let's say, here rather than here, which is a different point. And it seems like it should be a little better because we're evaluating a slightly more current gradient. We're not evaluating the gradient at time t, because we don't know what theta t is quite yet. But it's not theta t minus 1 either. It's like theta t minus 0.5, because we're doing sort of half of the adjustment of the theta to evaluate the gradient. So how hard is it to evaluate this? This is regular momentum. Is evaluate the theta times t minus 1. And the change for Nesterov momentum, and it's called that because a guy named Nesterov invented it, is Nesterov momentum says evaluate this, and I'm going to make this slightly different. Yeah. Instead of at theta times t minus 1, we do it at theta times t minus 1 plus lambda dt minus 1. Because that's the component what we will be using. Does that make sense or not make sense? So when we're updating our parameters, we are going to take lambda times the velocity, and there's two parts to that. And we are saying we're going to have this part that we move, and we have this part that we move. And to get a better idea of what this should be, evaluate this as if we move this part. That's it. Questions? Yeah. Are you sitting where you normally sit?
Nope.
Oh,
Actually,
okay. You're like maybe over here.
Right there.
Okay. Yeah, one. Yeah, that's a. Yeah. That's like just adding noise. Anyway, go ahead.
I'm still trying to see how, so before we wrote that theta sub t is equal to original theta minus lambda v sub t. I'm trying to see, are we just substituting in like, sort of, before we didn't have a substitute for the previous lambda? And
Yeah,
now
I
we
mean-
just have, I've used what it was before and what it's changing to.
The reason we're using these subscripts here that we haven't had before is we haven't really had to think about what is the value of it at certain time steps. We just know it's changing. So, right, in our code, it's just theta equals theta minus this,
Okay.
right? But to be more explicit, at the step we go through, the t step, we're calculating theta t from theta t minus 1.
And the change this time is that, this is the Nesterov.
With the Nesterovs, yeah. Where we evaluate this,
Yeah.
what theta we use to evaluate that. Okay. And it's halfway, it's not quite theta t minus 1, and it's not quite theta t. Can't be theta t because theta t depends on this. And so we'd have this recursive problem of finding what it is. But we do know theta t is going to have this component, and so we pre-use that. That's right.
Yeah, so you said that the higher beta is, the more it takes into account momentum.
Exactly. So the beta of 0 means don't do any momentum, right? That just says v of t equals this partial derivative, and then we just subtract that from here.
I'm just kind of confused where those equations correspond to the vector line drawings.
Okay, so let's do, so this should really have a beta here. This is sort of this is the beta vt minus 1. This is the 1 minus beta partial derivative of L with respect to theta at theta t minus 1. This one is so this is the final value we're going to use for v of t. Without momentum. Right, so v of t is beta v of t minus 1 plus 1 minus beta partial derivative. That gives us this final location. Yes? Here, this as well is 1 minus beta, beta v of t minus 1. And this is 1 minus beta times the partial derivative, again of theta, and this is at theta t minus 1 plus beta v t minus 1. Gotcha.
So how would you calculate that theta? Like look ahead and calculate that theta?
If you were using numpy, theta is a vector, right? This value is a vector. You would, so you normally have for this partial derivative, this is a function, right? Because we're not doing numeric differentiation, we actually create a partial, we have some formula or function for the partial derivative. So instead of calling the partial derivative at theta, right now we use a0 and a1, we would calculate the partial derivative or call the partial derivative with a theta plus this value.
Oh, so you would add that value to the coefficient.
We'd add, another way we could do it that's not as nice software engineering wise is basically before we calculate this partial derivative, add this value to theta, calculate the partial derivative, remove the value. Okay. Does that help?
So is theta discrete or continuous?
Is theta would be a vector of continuous values, floating point values. Okay. So again, from what we've seen so far, theta is basically our coefficients. A0 and A1 are our thetas, or if it's higher degree, if we have degree D, it's D plus 1, different values. So, we've got a ball rolling down a hill. We've got a ball rolling down a hill that looks ahead a little bit and sees where it's about to go and takes that into account on its next step. Okay? A ball with a little laser eye that looks out and adjusts its next movement. What we're going to look at next is learning rates that are different for different parameters, because that sort of seems like the idea, right? That we will have some parameters have different learning rates than other parameters based on how, well, there's a couple ways we could base it. One way we could base it on, like, if you've got a parameter that's changed a lot, you should maybe start lowering the learning rate. And if you've got a parameter that hasn't changed very much, you could start increasing the learning rate. And give by parameter, I need theta, I need a-slice. So the thought is, you should base the learning rate on the history of the gradients. And the idea is the learning rate, I'm going to just call it LR, of a parameter that's had a lot of updates, or a lot of large updates. So lots of or large updates. We're going to go ahead and say its learning rate should be smaller than the learning rate of a different parameter that has had few or small updates. So let's say we've got, in our one-dimensional case, we've got a parameter it's kind of just been looking like this the whole time, okay? We are sort of going down, but not ever very much. We're here, and we got a tiny little gradient, so we went here, and we got a tiny little gradient. Should we increase or decrease the learning rate? Susan?
Sorry.
So we're here, we just actually are starting, our gradients is in here. So here we go, that's our parameter, and this is the loss function that we see. It basically is really, really, really shallow. We take a step, and we go here. We take another step, and we go here. We take another step, and we go here on this slope that's negative 0.001 or something, I don't know. On our next step, should we take a larger step or a shorter step?
Maybe a larger step, because we want to see if there are going to be like slopes of like really high slopes.
Yeah. So I agree, there might be higher slopes. And if there are not higher slopes, this is so slow, it's such a shallow one, we should take bigger bites. You know, we should go farther each time because we're not getting any big gradients. And we may have a ways to go to get to a minimum. On the other hand, let's say we've got a more exciting parameter. It's, I don't know, like this. Okay? And we're going, and we happen to have a very large learning rate, which is good because we don't get stuck. So we happen to be going, I don't know, here, and then, you know, we go here, and then we go, I'm afraid we'll get stuck there. Let's get lucky. We'll go here, we'll go here, we'll go here, will go to here. We're making these giant movements. We probably want to decrease the learning rate. Or at least, it should be smaller than this guy. This guy, we know this guy's taking these. Does that idea make sense? So if you haven't made any changes, increase the learning rate to start stuff going. And if you have made a lot of changes, slow down the learning rate so that it doesn't go so fast. So that's the idea. So we can do something like this. We can basically come up with a separate learning rate for each parameter. So lambda sub theta sub I.
On this one, are we not like keeping going down constantly because we're just going to have the last gradient incorporated in our current velocity, our last change.
So let me back up a second. This is something that we were looking at, and we're now looking at another optimization. So this is per parameter learning rates, and we're actually looking at escalated credit. So we will come back to this, but for the moment, pretend we know nothing about momentum.
Okay.
And it will be interesting to see what this provides us, and then what if we add through momentum?
Now, if you get like large changes in like up and down directions, would you want to keep that large, or would you still want to make it small?
For the moment, we are going to start shrinking it if you have changes regardless of their direction. Even if they average out to 0, we're going to still reduce it. So I'm going to get rid of this. So this stuff we'll come back to, but let's ignore it for now. So we're going to say we're going to have our absolute learning rate, right? Overall, still a hyperparameter, but we're going to adjust it based on the history of changes we made, such that we want large changes to decrease our learning rate. Okay? And we don't care about the magnitude. So if we don't care about the magnitude, and we won't care about the size of them, how do we often deal with that? How do we deal with that in our loss function? We square it. So let's do that. Let's go ahead and take, let's say, the summation of the old gradients. Our notation is going to get a little confusing here, and I'm sorry. So we've got a theta sub I, which means the ith parameter. But now I'm going to talk about that at time k. So I'm going to just kind of put it like this, time k. So theta I, k, I is parameter number, and k is this one. So we'll take this over k equals 1 to t, where we're at time t here. And it seems like we should throw in a square root, just because these are squared. How does this look? What will this do? Will this give us smaller learning rates?
Haven't squared it yet.
Let's square it. Put some more parentheses around and square it. Thank you. Which is good because we probably want a positive number here. We'd be unhappy with a negative number. So if we have got a particular parameter that has not yet changed, has only changed a little bit, what will happen to this denominator?
Sorry, so the lambda and theta I, that's at time t.
This is actually at time t. Yes. That's a good point, because where the heck did this come from? So our lambda time t, so it's an important thing to look at here. We have a separate lambda for every parameter, and it changes at every time step. Or,
So you're actually adding up all the squares and then take the square root?
yes, we're adding up all the squares, and then take the square root.
Is it gonna make a difference if we put the sigma outside?
Yes. So, yeah, it would. Because if you took the sigma outside, the square root of the square is just the number itself, the positive. So it would be basically taking the sum of the absolute values, which is the L1, which is not what we're using.
So at this point, we're evaluating every time step as equal. We're equally treating all of them.
That's an interesting point. Does that sound good or bad to you to treat every time step?
Bad.
Which time steps should be more equal than others? The recent ones should be, okay, so we're going to put you on the Rmsprop. We'll get there in just a second. And by the way, this is called integrad, or adaptive gradient. So as you have got, if we compare two different parameters, and one is updated a lot, one has had high gradients, and one has had very low gradients, this will be a higher number in the first case, and a lower number in the second case, and therefore, in the first case, this will be smaller, total will be smaller, and it'll be higher. If we looked at the lambdas for a particular theta over time, so we've looked at time 0 all the way through time t, what happens to this value of lambda? Math. So we look at lambda, let's say it starts here, okay? We have, or let's just not look, let's say we're right here at time k, and now we're looking in the future. Can the learning rate decrease? Can it be less than it was before? Because let's look at the summation. Can the summation ever increase as we go to higher and higher time steps? Yes, it can increase. It can increase. Can it ever decrease? No. If you've got a sum of positive numbers, then non-negative numbers that can never get smaller as you add more of them in. So the denominator can only get bigger over time, which means the learning rate for this parameter is monotonic decreasing, right? It can stay the same if there's a 0, 1, and it can go down. So that's actually not ideal, I don't think. It's good in that if you have large gradients, the learning rate will go down. But if you have small gradients, it'll never actually go up. And there's something we have to fix here. Can anyone give me why we're going to have a potential runtime error here if we use this formula? Divide by 0. Exactly. If the sum is 0, like maybe at the beginning, then we've got a problem. So the fix is, don't make it 0. Throw like an epsilon in here. Epsilon plus. All right, just to make sure it's not 0. You'll see that a lot in these denominators, and it's all for the same reason, just to make sure we don't have to divide by 0. Now, since you brought up this question, we're looking at the past. Maybe we're a lot of time steps in the future. And we're still going to be looking at the past. It seems like there should be some statute of limitations, right, that says, you know, from more than 10 years back, I don't know, what, 7 years, it's no longer on your credit score, or your credit report, right? Or we have a statute of limitations for robbery. You know, if it's been however many years it is for that, 5 years, doesn't matter. So we could do the same thing here. We could say we're not going to start at time 1. We're going to start at some number of steps back. So instead of having a total historical, we can just say we're going to take the last 10 steps, 20 steps, 100 steps, whatever we want.
Can we not just distribute different weights for, like, how far is from the current time? So the furthest from, like, the further before, we're gonna have a weight that's, like, really low. And then for, like, the previous 1 or 2, we're gonna have a higher weight.
Wait. Let me see if I understand what you're saying. You're saying you want to count the most recent more, and the not quite as recent less, and the stuff in the far past way less. There's a name for that. What is it? Anyone? That is an exponential moving average. Right? The exponential moving average says we count one step ago a fair amount, and we count this next step before that a multiplicative factor less, and before that a multiplicative factor less, and so on. So, great idea, that's what we're going to do, and let's call it Rmsprop. Okay? But, yeah, if you forgive, so this is about forgiveness of old gradients. You don't change the past, you change the future. That's what we're doing for forgiving. We don't care about the past, we're trying to change the future and allow us not to care about what happened when this gradient was a baby. Right? The error is a name, yes.
Is there ever like a scale issue between like the lambda and the summation, where like it would always get lower or something, or it wouldn't like scale how you wanted to?
Well, you're definitely going to pick your lambda possibly differently if you're using ARAD or Rmsprop. It's a hyperparameter and its value may change if you're using this different optimization. So, Rmsprop, which stands for root mean squared propagation. The idea is we have a value which is going to be our exponential moving average of the sum of squares. So this exponential moving average of sum of squares is look very familiar to you. We're going to say it's some alpha times the previous value plus 1 minus alpha times the partial derivative of theta I squared. So here we're keeping a moving average of the gradient. This is keeping a moving average of the sum of squares of the gradient. And so then we just change our lambda to equal, again, lambda over square root of what? Anisha. So we calculated this moving average of the sum of squares. Why don't we put it in a denominator here then? Instead of our actual sum of squares.
The moving.
Sounds good to me. Let's put e sub t. Wait, not a sigma. E sub t. Minus what? No, t. And how do we deal with the potential 0 here? Yeah, add yourself an epsilon. We can add it inside or outside the square root, it hardly matters.
Can you remind me again why we're square rooting that?
Because we did here. Because it's a square. Oh, here's the real reason. Otherwise, it couldn't be Rmsprop. Right? This is a kind of a known value, the root mean squared, and so we just do it. But we would probably be fine without having that square. Other question? I guess without the square, we might be affecting the learning rate by large values here more than we would want. So we're kind of dampening it. Sorry, that was a question, Jack?
Sorry, can you kind of clarify again what exactly E sub t is in this case?
Yes. So E sub t is So what's this here? This is sum of squares, right?
Yeah.
If we divided this by t, it'd be the average sum of squares. And we could do that. We could do that. And that would be closer to this. This is not the real average sum of squares, but this exponential moving average,
Okay.
right? Where the old values are going down by this decay rate, right, of gamma. And so something 5 time steps ago, we have a gamma to the 5th of likelihood, yeah.
So we could just put like gamma to the t minus k in the
In where?
inside next to the square. We can multiply by gamma to the t minus k. Would we get the same thing? Like the square.
In here?
Yeah, in sum. times
Oh,
k.
I see. We could, yes, get the same thing if we threw in a gamma. So we'd have to actually throw in a gamma to the t minus k times 1 minus gamma, because we have a single 1 minus gamma here. And then we would divide by t. And that would be the same sort of thing. And also, this is nice and easy to keep, right? Just a single value that we have to keep here. I guess our sum could be simple too, because we could just store that in one value. But it just makes sense. We don't care about the far past. This is an easy way not to care about the far past and to care about the recent more than the not so recent.
How, like, what is the smallest value of that sum that you're adding in constant sum? Like, it has to be greater than 1, right? Because if it's too small, then you would be increasing revenue.
Yeah, so if you make it 0.0001, then yeah, that'd be bad. There was, I'm trying to remember, I don't remember which architecture it was, but some paper in the last couple of years, I think it was a Google one, so I think it was Inception, talked about the fact that 1 actually is a reasonable number for that. So it's not very epsilon-ish as we normally think about it, but 1 kind of makes sense in that if all these is 0, you're kind of leaving lambda alone. Whereas if you made it 1 times 10 to the negative 9th, then you're hugely increasing that lambda. That doesn't make a lot of sense. Okay, and then the final one is atom. So atom stands for adaptive, again. And I'm trying to remember exactly what it stands for. It's not some guy's name. Yeah. So it's adaptive moment estimation. I want you to think of it as Rmsprop plus momentum. Can anyone tell me what the moments are of a distribution as a statistical term? Does anyone know what the first moment is? All right, so just to know what his name is, it kind of makes sense. So the first moment equals the mean. And the second moment equals the variance. And there are more moments as well. So as you have more and more moments, you know more and more about what a distribution looks like. So we are going to be estimating these moments. Estimating the mean gradient. Have we seen estimating the mean gradient? Right over here, right, we had a exponential moving average of the gradient. Estimating the variance. We have right here the square, roughly variance. So we're going to make a slight change. But we have the sum of the squares here, right? So related to that second one. So basically, we have a V and we have an E. Okay, we're going to use them both. And part of what they do, so V sub t equals like the momentum. E sub t equals, let's just say from momentum. E sub t is from Rmsprop. And then they make a slight adjustment. So V sub t hat equals V sub t over 1 minus beta to the t. So the idea is, as t gets big, what happens to beta t? Beta to t? Given the betas between 0 and 1, it goes to 0, right? So it doesn't really matter when you're far up. But at the beginning, it is so what is going to be increasing or decreasing wherever we when t is 1, right, let's say, this will be a value somewhat less than 1. And so that's going to tend to increase this. So it is what I put it. So it's adjusting the earlier values to try and approach the what we call the true mean, let's say. Okay? And the same thing for the second. So we also do this for the second one. E sub t hat equals E sub t divided by 1 minus, except in beta, instead of beta, we use the gamma. Okay? So it's just consider just a correction, okay? An algebraic correction. And then our final learning rate is going to be like this. We're going to divide by the square root of E sub t, except instead of E sub t, it's going to be E sub t hat. And somewhere the V sub t has to come in. Where do we want that? Numerator, denominator? Thoughts, anyone? We want to make it like over here in the numerator. Except we need a hat. All right, it's a lot of algebra. Let's make sure we understand the main concepts. Concept number 1, ball rolling down a hill. That corresponds to momentum. Okay, that'll get us out of valleys and kind of move along. Second one we have, Rmsprop, the idea is we are going to reduce the learning rate if our recent average gradients is large. And increase if it's small. So unlike ADRED, we couldn't really increase. Rmsprop can go up and go down, which is nice. We talked about Nestor, and then we put them together. So we can put momentum together, along with this idea of looking whether we have large or small gradients. and how that should affect the learning rate, and combine them together, and that's that. With momentum, we talked about this partial look ahead when we're doing this addition, that we have a portion that is our historical and a portion that is our new. And instead of using the new, instead of starting where we are and looking at the gradient, first, we walk ahead to where we're going to move because of the momentum. We look at the gradient there, and we use that as a gradient again. This atom is Rmsprop plus momentum. What else could we add to it? What kind of momentum flavor do we have besides regular momentum? Nestro momentum. Can we use Nestro out here? We sure can. We would do that right here when we're evaluating this gradient. For the E sub t, we would then look ahead. Similarly, for the V sub t, we would look ahead. So we would do it for both. Actually, we would do it once and just square it.
Don't calculate it separately.
For the atom, we're like modifying the lambda, the learning rate, and then to modify theta, do we just do the theta like of I minus?
That's a good point. So we'll do, once we have our individual learning rate for each parameter, we'll say theta sub I equals lambda sub I, theta equals theta sub I minus lambda sub I times the gradient, times gradient. Okay. But we'll normally do this vectorized, right? Lambda will be a vector of lambdas. All right. On a simpler topic, we talked about binary classification. Let's talk about multi-label classification. So multi-label, let's say we have a picture coming in. Right? And we want to ask some questions about the picture. Has beer? Has hair? Has glasses? And happy. Right? So this comes in here, and we have 4 outputs. We could have an F that just has a vector of 4 outputs, let's say. So we're going to get a number for each one of these. Let's say this is number 1, number 2, number 3, and number 4. And let's say it's from negative infinity to infinity. We want to convert that to something between 0 and 1. What are we going to use to convert it between 0 and 1? Matt? Normalizing, not quite, right? What did we see on Monday as a way to convert this infinite range into 0 to 1? No, give him a helping hand.
Sigmoid.
Sigmoid with that. Right? If we take the sigmoid, that will take us into the range 0 to 1. And so this will then give us a number in 0 to 1. This is the probability of a beard, right? And the probability of hair, and so on. Probability of being happy. These are all independent, right? They're independently between 0 and 1. So we have decided what our function looks like, and then we're applying the sigmoid to get a probability for each one. What am I going to do for a loss? Raji, ideas for loss? Say it again. Cross entropy. Where exactly?
Is all of them separate?
All of them separately sounds good to me. So cross entropy here and here, and we sum them together, and we get our total loss. Right? So basically this will be our LC1, LC2, and so on. We sum them all together. Or,
And then this is assuming every label is independent of each other.
that's right. When we say the word label, we mean independent. It's like Gmail, right? You can put as many labels as you want. They don't do folders, they do labels, right? That's your model, right? So you can put multiple labels on things. And that's important. It could be 0 or all of them, or anything in between for a particular picture. As opposed to multi-class. So this is multi-label. Multi-class says I've got a bunch of classes, pick exactly one. So multi-class we've got a picture, and we've got to decide. We're determining emotions. So it can be one of, happy, sad, excited, disappointed. No, I like disgusted there. Disgusted. Okay? Can be exactly one of those. So we're going to shoot this through. We're going to come back with a number for happy, a number for sad, a number for excited, and a number for disgust. And let's say, actually this is coming into all these. Let's say the higher the number, the more we think that's what it is. So this might be 5 and 3 and negative 100 and negative 1,000. Well, we're probably excited. That's the biggest one. But like how much? And how are we going to do our training? Our input, we know, is one of these, right? Our input, our y, is 1 or 2 or 3 or 4, right? 1 or 2 or 3 or 4. Which class is it in? Although it's going to be useful to look at 1 as 1, 0, 0, 0 vector. 2 is 0, 1, 0, 0. 4 is 0, 0, 0, 1. These are called one-hot vectors. Why? Because there's one of them that's hot, that's on, and all the rest are off. So one is hot, all the rest are cold. So if we look at this, if we come out with a particular prediction for an x, and it's really this, we kind of like numbers here, where this is between 0, 1, 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 and we can compare against them. So we are going to do this. We are going to use e to the x. So take whatever number we got and do e to the that. This clearly is not giving us numbers in the right range. But we're going to sum all those together. And we're going to get a total. And then we're going to make another transformation and say this is e to the number over 1 over the total. E to the number 2 over the total. And so on. What do we know about this number? What range is this in? This is in the range 0 to 1. And this is in the range 0 to 1. And this is in the range 0 to 1. In fact, here's how we can view this. We can view this as the probability of being happy and the probability of sad and so on. If we sum them, what do we get?
Well,
We get 1. That's nice. We like that for probabilities, right? instead of coming out with, like, let's say this is a real happy, it is happy, our prediction might not be 1, 0, 0, 0, 0, right? It's likely going to be something like 0.7, 0.1, 0.05, 0.15, let's say. And we would compare that against 1, 0, 0, 0. And we're going to have a loss function to tell us how this looks. Does the concept make sense? All right. We're going to know two things. We're going to know what the loss function is, and we're also going to know how to do the derivatives back. We're not going to talk about those derivatives. We will, from now on, just let the software do those derivatives. But let's say y is 1, 0, 0, 0, and y hat is 0.7, 0.1, 0.05, 0.15. Our loss. An easy way to do loss is very similar to binary classification loss across interval. We're going to just take negative the sum over all I of y sub I, right? So this is going to be y sub 1, y sub 2, y sub 3, y sub 4. It's either 0 or 1. Times, any guesses? ln of y hat sub I. So if the y's and y hats are identical, we're going to get 0. And we're going to have error from each of these terms. One of them is going to get us error from how far, sorry, back for a second. We're going to have an error, these terms are going to give us no error, right? Because these are 0. So it's only going to be the one hot part. And we're going to say how far away are you. So if this is 0.7, we really don't care what the rest of it is. Right? I don't care what the rest of the stuff you said. I care about the one that you're supposed to be getting right.
Couldn't you theoretically care about the rest though? For example, your model is getting confused between only happy and sad or something. Like, then you might want to adjust differently than if it was like.
Possibly, maybe you'd say, for instance, if this is 0.7, you'd prefer these all to be 0.1 and not, although it's not really, we don't normally care. Actually, we just don't normally care. All right. That's multi-class and multi-label fairly quickly. The last thing I just want to talk about is training validation. Why do I validate a validation data set? Because we can easily overtrain on our training set. So we have a bunch of hyperparameters. You've got more of them today. Betas, gammas, and epsilons. If you keep using the same validation set, and you try a different set of hyperparameters, and you try a different set of hyperparameters, you try a different set of hyperparameters, and you try over and over and over again, until you get one that works well with that validation set, guess what you're doing? You're training to the validation set. So you don't know anymore how you're going to generalize. Okay? Because you picked the best possible one to generalize to the validation set. So you need another set. You need what sometimes called a test set. Confusingly, it's sometimes called a validation set. But let's just throw that for a moment. So a test set or a holdback set. And you're allowed to use it one time. When you're done. You're done all at the end one time, and then you say, okay, how well is this going to generalize? I'm done. I can't make any more changes, but how well is it going to generalize? And you test on that last holdout set. And since you only did it once, you're not training. You're not teaching to the test, right? That's really what we're doing in the case of the validation set, is we keep trying, retraining, teaching to that validation set. And it might be the random particularities of that validation set, which won't generalize to the real world. So we always have actually 3 sets. In a test set, the idea is, look, you lock it away, you promise yourself you're not going to look at it until you're about to publish your paper. Right? And if it shows you don't generalize well at all, you're not happy. All right, so I got homework for you. I've got quizzes. I don't think I handed out to everyone, so you got some homework. And then there is an assignment, which is available from the schedule. Basically what it is you've got let's describe it briefly. We have a 4-degree polynomial where we are trying to use that as a model to fit data that actually came from a third degree polynomial. Your goal is to both speed up the training and reduce the loss. So I have given you something that trains in 4.5 minutes with a certain amount of loss. You need to cut down to less than 1 minute with even less loss. What are you going to do? Regularization, fancy optimizers, change the learning rate, change the number of epochs, although that's going to increase your time. We do have 2 leaderboards, so as well as you've got to get to these specific minimums, you can put your name on the spreadsheet if you got better than that, and we'll have a small prize when you turn this in on who had the best, either the least time to get to the desired loss or the least loss overall. I don't care how much time.